architecture, microarchitecture, and ISA for GeneSys. And as he mentioned, let's keep it interactive. If you have any questions, please feel free to interrupt, and we can discuss as we move forward. Just a little bit kind of background on myself. I was a former PhD student at the ACT Lab, and I graduated about a year ago. Now I'm a system architect at Apple BPG, working on architecture design and compute acceleration strategy for next generation spatial computing and AR/VR devices. And throughout the GeneSys project, I was kind of lead architect on the architecture for GeneSys, ISA, and microarchitecture. So in this part of the presentation, we'll go through what the architecture looks like for GeneSys that enables the end-to-end execution of complex neural networks. We'll talk about the ISA, how we can use the ISA to program the accelerator, and how we can use the compiler to kind of generate kind of instructions and manage the execution. And we talk about what's the parameterizable templates that we designed for the GeneSys architecture. And in the next part, Hanyang will talk about the verification infrastructure and how we implement the accelerator on FPGA and ASIC, and also how we do profiling based on that. So let's talk about the overall architecture and the way that it looks like. On the right, you can see there are two main kind of processing component for GeneSys. There is one systolic array, which is similar to any systolic array that we have seen, like Google's TPU, for example, that's in charge of performing all the convolution and gem-style operations. And on the bottom, we have the Tandem processor that is a specialized yet still programmable companion processor that works with the gem unit and is in charge of processing the operations that are non-gem, that you cannot map them to the systolic array efficiently. So it's in charge of those operations and also managing the whole end-to-end execution of the accelerator. So this is not only does the operations, but also handles synchronization with the gem unit and also the overall execution and orchestration of it. And overall, in terms of the memory subsystem, we are using mainly software-managed scratch pads. As you know, neural networks are generally, they have a regular structure. So the structure of data accesses can be kind of defined at the compile time. So that's why we rely on a software-managed scratch pad to leverage that feature. And these software-managed scratch pads, they come with a programmable off-chip memory interface that is in charge of bringing the data in tile granularity to the accelerator and also storing the data. So first, let's talk about the systolic array architecture. As I mentioned, it's a 2D grid of processing elements, and each processing element is merely a multiply add unit. It does multiplication and accumulate the result in a register. And the overall execution is, on the left you have your input activation buffer. You access the inputs. Inputs are forwarded through this way to the processing engines, and each input is shared with multiple processing elements. Each processing element has an individual weight bank buffer. So where you get an input, it's shared across multiple weights, kind of horizontally, and you do the multiplications on processing engines, forward the result to the next processing engine, and you accumulate the results in your accumulate buffer. So the way that it works is that you get a vector of input, you have a matrix of weights, and at the end you get an output of a vector to matrix multiplications, and you accumulate in your output buffers. And you continue doing this until you finish the execution of vector to matrix multiplications. As we mentioned, this is the systolic array, but we implemented it as a template. So it's fully parameterizable. The dimensions of the systolic array, you can pick and choose any dimension that you would like. The bit width of the processing elements, it's also programmable and parameterizable. You can design them to do 8-bit by 8-bit integer operations or 16-bit integer operation. I think the current implementation supports integer, but the design can be extendable if you want to enable brain floating point or any other sort of floating point operations. And also the size of the basically the data path across the processing elements is also programmable based on the bit width that you select. And the systolic array is also, since we really kind of capitalize the opportunity that you can at the compile time program and orchestrate the execution based on the data flow of the neural network and the operations that you have, we can program the systolic array to perform any and support any form of data flows. You might have heard about input stationary data flow, weight stationary data flow, or output stationary data flow. And all those things, the way that it means is how you program the loop of a convolution, how you order the loops of a, there's a 7-nested loop for any convolution, it's how you order these things. And the architecture allows the compiler to leverage on that and choose the best optimal data flow based on the given neural network and optimize the execution and on that. And the architecture is flexible to support that data. Talking a little bit about the memory structure of the systolic array, you have the input activation buffers that are used to store the inputs of a single layer. You have the weight buffers that are distributed across the PEs. Each PE uses an individual weight buffer bank that you store the weights of a convolution layer or gem matrix multiplication layer. You have your output buffer that they collect the outputs. And we have also kind of a vector buffer for the Tandem processor. I'll get into that in more detail. And of course, you have instruction memory that you store the instructions. And the way that it generally the execution happens is we have sequences of fused layers. I'll explain how they work. But at that granularity of those layers, you load the inputs to the input buffer using a set of programmable memory interfaces that we have from the off-chip memory. You populate the inputs, you populate the weights, and then we have on the chip we have kind of an address generators that at compile time you figure out what's the pattern of accesses to the inputs and to the weight buffers. And on the fly, we just program, we have instructions that you use to program those address generators, and those address generators are gonna be, when you configure them, you're just gonna hit, they're gonna generate the addresses, and they're gonna be basically getting the data, and you can do the computations on the systolic array. So everything happens kind of, there is no actual instruction to generate addresses for you, it's just a set of configuration instructions that you use, program, and then run the execution. So now I want to spend some time on talking about the Tandem processor, which is the companion processor that works with the systolic array. But before getting to that, if there's any question up to this point, let's discuss and then we can go.
Yeah, I have a quick question. So you said the systolic array supports like multiple data flows. Are those at compile time, as in like when you're at design time? Or is it at runtime?
So it's at the compile time.
It's when you are like designing, when you're generating
the instructions. So the compiler is in charge of that to understand for each individual layer what's the optimal loop order that minimizes the number of off-chip accesses. That's the main optimization that the compiler is looking at. Trying to minimize the number of off-chip accesses and decide what is the maximum kind of data type that we can leverage on reusing that. And generates the instructions, basically generates the loop order that we want to do. So the loop order, kind of, that's where, based on that loop order, we program the address generator. So it's all on the compile time.
Yeah, I think what I meant is like, so when you are designing, when you're creating a design.
When you create the design, you're going to be using the template of the systolic. That template supports everything for you.
The template supports everything.
Supports everything. It's just, you choose to, I don't know, the dimensions of the template. You choose the bit width that it supports. You choose the size of the input buffers, output buffers. These are the parameter you choose. But any systolic array, if you choose a 2x2, let's say systolic array, it supports all those data flows, and the compiler needs to kind of manage that based on the DNN that you are compiling.
So is there going to be some overhead like associated with supporting all these different data flows? So for example, say if I only want to do one data flow.
You can choose to do that. It's just a matter of how you order the loops. So how you put the order, and that's what the compiler is going to do. There is no specific kind of overhead at the hardware level for that. It's more like exposed at the software level, and the software is supposed to do that, and that's embedded in the compiler. So you don't have to deal with it. So compiler just supports that. Yeah, go.
So now you said that the compiler takes care of loop ordering. So if I'm getting it right, is this somewhat like a TDM-like model where you have generated stencils of different loop ordering?
So kind of similar. We are just looking at our own specialized ISA for that, but it's kind of similar. The compiler does a kind of a search over the combinations of those loops and figures out what's the optimal loop order. So to some extent, it could be similar to the compiler optimization passes in TDM.
Yeah.
But yeah.
But isn't that going to be like a severe overhead in terms of compilation time? Is that
So
do you factor that in, or is that not?
So first of all, it's a cost that you only pay at the compile time. So at the execution time, there is no cost associated with it. So I don't know how long it takes these days to kind of compile a program on a neural network.
The biggest demerits of TDM
Sorry?
The biggest demerits when TDM is discussed is that their stencil approach, it takes a lot of time to kind of create these stencils and then run these stencils, and they kind of and half of the stencils are actually, they don't make sense.
So exactly, so that's a really good point that you made. So what we do is it's targeting the architecture of the GeneSys. We try to prune first the search space. So some of these loop order might not make sense. Some of the loop tiling dimensions might not make sense. For example, usually you use power of 2 kind of loop tiles. So we first prune the search space and using some kind of using some heuristics that we have. And then I think the search is right now is more like an exhaustive search over these different combinations, but Chris can talk about it in his part more. So we're going to talk more about the compiler later. Chris is going to cover that, but I think that's at the high level.
So I don't see SRAM memory on the card on the option is there. Why you decide so? So anytime when you see some SRAM memory on the card.
So this is the off-chip memory. So this is the DDR is completely off-chip.
But do you have something smaller?
Yes. So that's what we call it, like an input act. This is like one on-chip scratch pad. It's an SRAM dedicated to store the input data. Yeah. Exactly, input activation. We have the weight buffer. Weight buffer are actually, I don't know if you can see them here. It's like behind this. Those are storing the weights for you. And we have the output buffer, again, another on-chip SRAM that collects the output. And we have these off-chip memory interfaces that either bring the data in or kind of drain the data.
You do this for each layer. You do load data for each layer, compute everything, and then write back.
Exactly.
You allow multiple layers to produce intermediate data on chip, and then keep doing without need to go back to post.
So what we do is, I'll talk about it later.
Okay, this is what is coming.
More in detail, but what we do is that at the compile time, we decide a sequence of layers. You can imagine it could be a convolution followed by a redo and an add, like a residual add that you have. Let's say that's the sequence of operation.
Okay.
And then we break it down into tiles of computation. So you load a tile of data, you do the convolution operations on the systolic array. Whenever that tile is done, you pass it to the Tandem processor to handle the redo and the add operations for you. And then while it's happening, you load the next tile to the systolic array. So we do software pipelining at the granularity of a tile so that you can leverage leverage the computation at the nodes that we have. And yes, you execute a sequence, and then you execute the next sequence, you execute the next sequence, you execute the next sequence. And the sequences are defined at the compile. Alright. Any more questions?
So in general, when you said that multiple data types and supported on each processing element, right? What would still be the native unit of computation? Like, let's say if I have said that I want to support 8.4, 8.8 and just make up 8.16 as well, right? Would you still, and one model is compiled in 8.16 and the other is compiled in 8.8. That means like each processing element would be half as rich?
Oh no. So it's flexible at the template level, but when you generate the hardware, it's always fixed. So either you choose to generate a GeneSys instance with int8. So the multipliers are all then int8. So you cannot do int16 with them. If you want to do int16, you have to do it temporally, do partial computations and temporally aggregate. Or you just choose to generate a hardware. So it's not runtime flexible, as like you can do a kind of generate a hardware, do an int8, maybe you choose another DNN, do an int16. You should choose. When you do that, at the time that you generate the hardware, you will either do one or the other. Cool? Alright. So then yeah, let's spend some time on the Tandem processor. We're going to discuss it in more details because it's more like a newer thing. And as Hadi mentioned, we have a full presentation on this also, I think Tuesday evening, that we talk about the Tandem processor. But I kind of give you a highlight of it today as well. And the reason behind that is, so if you look at the majority of the research on the deep learning accelerators, the papers over the last decade, there's been tons of papers on accelerating DNNs. They usually talk about how you accelerate the gem or convolution operations. I remember even if you, I think it's called 2016, it used to be called International Conference on CNN Accelerators, because people were only talking about how you can, International Conference on Convolution Accelerators, how you can accelerate convolution and gem operations. And the reason behind that was, back then if you look at the older neural networks, the majority of the operations, 99% of the operations were convolution. So it makes sense that people focus on those, and there has been tons of research on how you can leverage quantization, how you can leverage sparsity, how you can leverage in-memory computing, analog computing, so any sort of acceleration to accelerate convolution and gem operations, and any form of data flow optimizations. But as DNNs evolved over the last few years, more and more non-gem operations started to kind of emerge. For example, if you look at the 2014 timeline, these were the only operations that a neural network had. You would have convolution, gem, and only ReLU, max pool, and average pool. And there were like very small number of those in a neural network. But ResNet came in, residual add became a thing in almost all of the neural networks. Then later on with mobile net and efficient net, those types of networks, depthwise convolution became a new thing. It's convolution, but at the end it's not a matrix operation. At the end it's a vectorized form of operation and a reduction-based operation. And now, as you can see in large language models, transformers, there's tons of other operations. You need to deal with transpose, you need to deal with reduce mean, GALU, softmax, all those things need to be done. So, as I said, these non-gem operations grew in diversity, and also they are interwoven with the gem operations in very complex architectures. So what we really did here was, when we were designing the Tandem processor, we wanted to see what the best design that we can do. Because generally, there are two approaches towards supporting the non-gem operations. Either designs use more like a general purpose vector processor on the chip. For example, Google TPU is similar to that they have this vector processing unit. It's more like a general purpose. There are some level of specializations, but it's mainly general purpose vector processor. Or you use dedicated units. For example, if you can see a lot of the designs, they show, okay, there is a ReLU unit, there is a pool unit. But the problem with either of these approaches is that if you do a general purpose, you're gonna lose performance, because at the end you wanna accelerate to the end, you wanna accelerate the whole neural network execution, so you're gonna lose performance. If you use dedicated units, your hardware might become obsolete, because as I mentioned, new operations are coming. So, and then your accelerator is not going to be functional to support those. So if you want to support, you have to then either use an off-chip processor to accelerate those, or you cannot just support it. So what we really did here was try to balance this specialization and programmability to design the Tandem processor. And the approach that we took was ISA specialization. But how we did this, let's go through an example of a vector add with a general purpose ISA. This is literally taken from the RISC-V manual, and this is how you can do a vector add operations. But let's see what are the real bottlenecks of this operation. First, you have some sort, since it's a general purpose ISA, it's used as a register file to get the data and process on that. There are a couple of instructions that you need to use to just increment over address so that you can load vectors to your register file and do the operations. You need to bump the pointers to get the next data when you are loading the data into register file. And we profiled it on the range of neural network operations, and we saw that these instructions that are used for address calculations can kind of lead to about 40% overhead into the end-to-end runtime. Another class of instructions that you would need, just the instructions to load the data to the register file. Now you know where the data is, but you just need to do a load operation or a store operation. So these instructions also cause about 20-27% end-to-end runtime error. And the last class is loop management. So we are dealing with a lot of nested loops specifically. This is the example is like a one level of loop, but generally in neural networks we are dealing with nested loops. So you have to also manage the loop execution, keep track of the iterations, and also use branch instructions to do the loop management. And that's also caused about 50% end-to-end runtime overhead. So in summary, what we really see was the main problem with using a general purpose ISA for accelerating these non-gem operations is you are using a register file at the end. So you have to kind of consume instructions to get the data from the register file to the compute unit. So what we decided was, why not just have a scratch pad? They can be software managed scratch pads, because at the end we know the regular access patterns of the DNNs at the runtime, and let's directly operate on a scratch pad. So let's design a processor, could be similar to a general purpose RISC-V processor, but instead of having register file, let's just directly access the scratch pads and get the data from the scratch pad. But as you can see, there's going to be a key challenge with that. Now you need to have all the addresses to the scratch pads at compile time, and you need to fit them in your instruction board. In a register file centric ISA, you have register index in your instruction, which is like usually like a 5-bit or 6-bit kind of, depending on the size of the register file. But now I need to access a scratch pad. A scratch pad could be pretty huge depending on the size of the accelerator and the size of the NPU that we are generating. So how can I fit those addresses in my instruction board? I still want to use a 32-bit instruction. So what we can do? The insight that we thought was, let's introduce a concept of an iterator table, and let's put that iterator table at the front end of the Tandem processor. So at compile time, let's figure out, the compiler can figure out what are going to be the access patterns to these vectors or tensors that the Tandem processor is going to use. And then at compile time, you can generate the offsets for these things and also stride. Because at the end, we are dealing with strided access patterns. It could be more nested, you could have different strides based on the nest of the loop nest level. But at the end, it's like kind of strided access patterns. So let's figure out all those things at compile time, use a set of config instructions for the Tandem processor to config these iterator tables. Then during the computation, we can only have iterator indices to these iterator tables that you just index this, get the offset and the stride, and have another pipeline stage that's just do the offset process stride, get the address for you, and do the computation and access the scratch pads based on that. So the real insight is now I'm kind of doing a indirected access to the scratch pad. Instead of putting this address in the instruction, I'm just putting this index. Index again is 5-bit, so I can still have a 32-bit instruction, get the offset and stride that I need, do the additions, and get the data based on that.
So, so it's basically just as if you replace the register file by just the iterator table, right?
So register file is.
But it's not a vector register file.
Yeah, this is first of all, this is not vector because it's a single iterator table, and you are storing this offset stride information. So kind of similar from the instruction, the config instruction perspective. Yes, instead of using like register 1, register 2, register 3, you say index 1, index 2, index 3, which is indices to the iterator.
Just to confirm, you saying that Tandem does not have vector registers?
It doesn't have vector register file.
Doesn't have. Okay.
It doesn't have vector
It
register.
doesn't have.
It uses
It doesn't
scratch
have vector
vectorized.
loads.
Sorry?
It doesn't have vector.
No, there is no
wow,
vector
okay.
load, vector store instruction. These are all. I'll show you what the instruction format is, so that you can make it in 2 slides. Okay? Shall we move forward? Now, before getting to these instruction formats, let me also introduce a new concept. Now, as I said, we are eliminating the register file from the design, and we are just using a scratch pads. But if you look at the Tandem processor, we need to define multiple namespaces for the Tandem processor, since we are not using a vector register file. We have 2 namespaces, which we call them interim buffer 1 and 2. These are the scratch pads that the Tandem processor can use to load data from the off-chip memory, do the computations. There could be multiple rounds of computations, write to these scratch pads and buffers, load the data. We have an immediate namespace, so we don't have immediate in the compute instructions, because still we wanted to keep it a 32-bit. What we do is that we have at the beginning of a block of instructions, you have some config instructions. You fill your immediate namespace with those immediate values that are going to be used, and then during the execution, you just access to this immediate namespace. And also, yeah.
Just a basic question over here. Why is like changing your vectorized register file to scratch pad give you such high energy efficiency? Like, is it something to do with the way register file, vectorized register file is designed or accessed?
It's just about the number of redundant accesses that you do. So in a general purpose ISA, you are getting the data to you are just sending instructions to get the data into your vector register file, and then compute on the vector register file. While we are saying that you're actually losing instructions because you don't need to do it, let's just use a scratch pads. And I want to emphasize that this is because we are accelerating machine learning neural networks. You need to have a register file in general purpose processor, because the accesses you might not be able to do, figure out the access patterns or at the compile time. But since we are targeting this class of models, now we can do it. So you can figure out all with the software at the compile time all the access pattern, and let's just directly access the scratch pad and don't lose instructions to get the data from to the register file and then compute on the register.
So basically, you are getting rid of that in direction using
Exactly.
this scratch pad.
Exactly.
Okay, that makes sense.
So essentially, you are making that assumption that you have like a fixed type of access pattern.
Yes.
So that's
Fixed in a sense that still I can do many sort of different loop orders, different strides, all those things can be programmable, but under the assumption that I can figure out this order at the compile.
something like an affine access for like in addresses. So like essentially the vectors like or essentially the scattered accesses which you have can have a affine location, and like essentially can be converted to affine at compile time and then just
Yeah.
So that's the assumption, and that's where you're gaining from say general purpose vector.
Yeah.
Before compile time, we can have different patterns of access. But
Yep.
after compile time,
Yeah, so compiler just figures out, okay, if you are running this operation, this is the access pattern that it's going to have. It is based on the operation size, the input output size, based on the architecture. As I said, it's a template. These are all templates. You can have a 32-bit wide kind of lane of CD for the Tandem processor, or at the end it's a vector processor, so you can have different lanes. Based on those configurations of the hardware, operations of the operations of the neural network, compiler decides that this is the access pattern to map that operation to the processor. Right? If no question, okay. One thing that before, so these are the namespaces that the Tandem processor needs to do. Now, I wanted to also emphasize the Tandem processor also works with 2 namespaces of the Gen unit as well. One is the output buffer. So, as I mentioned, we do the software pipelining. We execute one tile on the systolic array, another tile on the Tandem processor, and we do the software pipelining. To maximize the utilization, what we do is the output buffer can be exposed to the Tandem processor. Tandem processor can directly read from the output buffer and do the computations on that. So that's another namespace. So instead of having the FIFO between the gem unit and the Tandem processor, or instead of using move instructions to get the data, let's just use that output buffer directly. An output buffer is also double buffered, so you are not accessing, your gem unit is accessing one section of the buffer, is accessing another section. So there is no kind of congestion on the accesses, but with this you can directly consume the data and improve the performance. Another thing is, now if you are expanding in the sequences of the instructions, the sequences of the layers that you are processing, the output of the Tandem processor can kind of move its output to the input buffer and prepare it for the next layer that you want to execute. So that's why we have all these namespaces available to the Tandem processor to either read from or write to. Go ahead.
So with this, I understood what you are saying about that double buffering scheme. So what if some layer that you have in your neural network, it doesn't have a lot of data reuse. So like have you seen your architecture getting stalled? Because even with this double buffering scheme, you were not able to properly fetch the data from the next layer. It was just still stuck in fetching the next set.
So there could be, yes, there could be some workloads that actually, for example, if you are just doing the matrix-to-matrix operations, you don't have much data reuse. So that could happen. You're going to lose cycles on just getting the data. But that's just the physical limitations of the chip and the bandwidth of the memory that is available to the chip. So that could still be. But double buffering is usually necessarily, specifically if you are tiling the computation, because imagine if you were able to run all the computation on one hit, so just get the whole matrix to the accelerator, compute it and store it, then yeah, double buffering would not make sense. But since we are making the accelerator flexible in different sizes, specifically if you are targeting an edge application, so you're going to have a smaller design because of the limitations of your power, budget, or area, or whatever. In those scenarios, the size of the scratch pads are going to be small. So you cannot load the whole matrix in. You have to load it into the tiles, and double buffering enables that software pipeline so that we can boost it.
Yeah, that was basically my question was basically if you are running some layer, right? And by some configuration issues, are you able to detect that at the compiler level, and are you inserting some no instructions so that you don't you don't basically compute the wrong
Totally. Compiler does those kind of instruction dependencies as well, and actually can insert no-op in the Tandem process.
You insert synchronization point, right? Wait, synchronization, just
yes.
wait.
Like in GPUs, those synchronization primitives are already taken account of because of the advanced software stack.
So we do also have, okay, so let me get to that one. I think we have these synchronization instructions as well.
I just wanted to check if they accounted for that.
I got to follow up. Is this in order process? In other words, everything happens.
Everything is in order. No.
Both
Yeah.
systolic array, but sometimes systolic array gives results in some not predictable time slots, right?
Actually,
So
no,
I'm
the
saying
accesses of the access, the order, the way that the data is going to be generated, you can actually profile it at the compile time as well. So you could really know at what specific cycle what data is going to generate. But we have the synchronization instructions.
Yes, it's
let me
important.
get to those that enables the synchronization between the gem unit and the Tandem processor. So I'll get to those instructions if I make it more clear. All right. So now let's look at some of the instruction formats that we have. Let's first talk about accessing the scratch pad. That's what we call it recoupled access execute, and it's kind of in contrast with decoupled access execute. In decoupled access execute, you have a processor that just does the access for you and get the data, and you have the main processor that does the computation. What we do, the way that we design the ISA for the Tandem processor, is kind of we are merging these two instructions into a single instruction. So in a single instruction, you get the data and also compute on the data. That's why we call it recoupled access execute. You have two classes of instructions for managing accessing to the scratch pads. One, we call it config instructions that are used, as I mentioned, to config those iterator tables with the base address or offsets and the strides. And we have the compute instructions where you express the compute operation and also the indices that are used for either of your operands or destination, basically either the source operands or results. You just express the indices, and these indices are used to access that iterator table on the same instruction and the same pipeline, get the data, and next cycle do the computation. So let me show you the pipeline, and that might make it even more clear. So this is the pipeline that we have for the Tandem processor. Similar to any processor, you have the instruction fetch. You fetch the instructions. Instructions, there are two ways. If it's a config, it's either go to the iterator tables and fill out the iterator tables based on those accesses that we have. And this is just a preamble. You run it once, config the iterator tables with the accesses that you have. And then when you are running the compute operations, you use the indices to access the iterator table, get the offset and stride. On the next stage of the pipeline, we just have three adders that you do the stride and address calculations, add offset plus stride, get the address, then feed it to the buffers that the Tandem processor uses, either if it's the output buffer of the systolic array or if it is the interim buffer that for the Tandem processor. Get the data and then do the computations using ALUs. So I want to also emphasize on a point that usually in a vector SIMD processor, you have all the ALUs on the same stage. So you get the data, it's just you do single instruction, multiple data. We still do SIMD, but the difference here is now we also have another level of pipelining across the ALUs. So we interleave the accesses to the scratch pads with the computations on the ALUs. And the reason that we need to do this is in a SIMD processor, you use vector register file. Register file is small, usually is close to the ALUs, so you don't have usually frequency problems. But since now we deal with the scratch pads in different parts of the chip, it could be the output buffer, it could be the interim buffer, and these are relatively large memories. So since we are going to minimize the length of the wires of the system, that's why we do this interleaving, so that you don't create critical path for the frequency optimizations. And the accesses can be just forwarded across these ALUs and across these banks of your buffers internally within the processor to maximize the frequency. Okay, go ahead.
Can you explain how data comes from off-chip memory into these buffers and how do they leave?
Okay, yeah, I'll explain the instruction format, but let me tell you what this is. So we have, actually I should have mentioned these things. So we have a data access engine that is in charge of bringing the data from the off-chip memory or storing the data from the interim buffer to the off-chip memory. So again, on the instruction, we have some instructions to config this data access engine with the access patterns of how to bring a tile. Then you get the data, fill out the intermediate buffers. So the intermediate buffers are those kind of medium to work with the off-chip memory. You fill the intermediate buffers. After finishing those instructions, then you go to the compute instructions where you access these scratch pads, get the data, do the computation, and then at the end we have the instructions again to configure the data access engine to kind of move the data from these units from these buffers to the off-chip memory. We also have a permute engine that is used for handling tensor layout and permutations of the dimensions of the tensor if you require. For example, you want to do transpose operation. And we also have a cool code repeater, which is for handling loops, which I'm going to get into. But that's how we get the data from the off-chip memory, and we can see the instruction formats for it.
So you have something like a vector load, except it's not at the vector level, it's at the whole tensor level.
It's at the whole tile level. So not tensor, it's at the whole tile level. So its cost gets amortized across a tile as across a small vector that gets to the
So you're compiling.
And it's like more like a kind of implicit rather than explicit vector load instructions, because it's just config. You just config, you hit go get the whole data. Okay, data is ready. Now let me do the compute. That's how it works. It's more like an implicit load store rather than explicit vector load vector store instruction.
I see the design, but one comment is vector loads are typically can take 10 cycles, right? Now you have scratch kind of loads, could be, I don't know, 3 times. Do you have idea how more compared to loads from registers? So in order to make this scheme performant, not correct is fine, performant, you must have a lot of overlap because basically those load from scratch memory can take 30 cycles.
Exactly, so
And then
that's
you
how we
have
do this
a
software.
lot of overlapping
Totally.
pipeline. Otherwise, just a lot of weight.
Totally.
To start, yeah.
No, that's exactly what we
So
do.
it's good to
that's-
see some performance data. I mean, from real machines.
Yeah, so we have actually some data I can show you at the end
Okay.
on how we get compared to that. Yeah.
Yeah, I wonder if the ALUs can also take input from other ALU this type.
Oh, that's what we don't support that. So you mean like getting ALU from node? It's like all the ALUs are individual. They do just do one. They share the operations, but not the data.
Yeah. So the follow-up question is, for this design, compared to a more traditional design with the scratch pad and the vector register file, we will have usually a smaller SRAM or other physical implementation as the vector register file. And then if you can reuse some of the data inside the vector register file, that may give you some energy saving compared to if you store and load data from the scratch pad for each time, because the scratch pad is physically larger. And
You made a really good point. I wish I might have it as like even a slide. Let me find if I have it. So I get what you mean. So that's why you have vector register file in general purpose processors. But let me how we can let me show you this instead. Okay. So this is actually what we see. It was I skipped this slide because of the time limitations. So when we deal with these non-gem operations, there is actually a small amount of data. So these operations are generally mainly memory-bound operations rather than being compute-bound. So the actual locality that exists in these operations is very, very small. It's not like an operation that it's on a register. You don't have a register file and you store the data and access it, I don't know, 20 times or just leverage the locality. It's not the case for these non-gem operations. Imagine imagine the residual link in ResNet. There is just an add operations there. You load the vector, maybe another vector exists already on the chip. You do the additions and store. So you do lots of load or stores to get the data from off-chip memory, but we're only doing just an add operation. So there is not much data locality available. And that's why a register file would be suboptimal for this design, because you don't have locality to use it. So why are you spending cycles and just getting the data to the register file or training the data from register file? Make sense?
Yeah.
So I think you mean access time to this large register, scratch pad compared to small register is more, but because we exploit more actually locality and the data reuse in large scratch pad, it compensates those latencies.
No. So what I mean is,
because
let's say if you have data locality on your register file, you get the data from a scratch pad, store it in register file. Accessing register file is cheaper than a scratch pad, and you might access that register file, let's say 10 times. That's how you get benefits in a general purpose processor. But what we do here, we are dealing with these non-gem operations that the locality is very small. You just access the data once, you just do one computation on it, and you are done with it. So anyway you have to make that access to the scratch pad. While you're doing that access to the scratch pad, let's just do the compute at the same time without going to register file, and then just be done with that data. So that's how I'm kind of making that differentiation. Make sense? So let's move a little bit faster because I think we are. So I think I talked about these instructions. We looked at the thing. So let's talk about also how we balance specialization and programmability. I talked about how we specialize the ISA for accessing data from scratchpads. But at the end, as I mentioned, these non-gem operations are growing in diversity. So we want to also have support programmability on the processor so that we can support this. That's how we kind of design our ISA for the compute operations. So we have two classes of operations that the processor currently supports, and it can be extendable. But right now we have a set of primitive operations, simple add, subtraction, multiplication. We actually have a MAC operation as well, can be used for the depthwise convolution operations, and some also some kind of logical operations, not and or, and also we have a no-op, which compiler uses whenever it inserts these no-ops whenever it tries to remove instruction dependencies in the processor. And also we have higher order operations such as sigmoid, tanh, which we use lookup tables to implement these things. And also some other operations such as apps, sign, floor, and seal. These are the operations that we saw that were more frequent in the benchmarks that we were looking at. That's why we implemented those as higher order instructions, so that you can run those with one instruction. These are more complex, similar to these primitive operations. And to support more complex operations, we kind of use macros. Let's say if you want to support clip operation, it's a kind of a activation function. It can be supported with a max and a min. So it's a combination of primitive and higher order operations. For example, GELU can be implemented with a number of multiplication, addition, sign, apps, and absolute and min, or softmax can be implemented with a combination of these primitive. So we have this primitive operation, and whenever there needs to be support, we have operations that are more complex, we can use this combination of primitive higher orders to write macros, and use those macros to support these more complex.
So here, for example, vector register will help, because
so sure, yeah, I would assume for like a softmax.
This area, right?
Yeah.
This area, right?
Yeah, I mean, I would assume there could be kind of operations that you have multiple accesses. But again, you are using this processor to support.
This is design decision.
Yeah, exactly. Cool. All right. Now let's talk how we support nested loop operations. So these non-gem, you don't do just one vector add. You are doing, you are looping across a tensor to support the vector add. Again, for loop operations, we have explicit loop instructions, and they are classified into two classes. We have one class that, again, it's a preamble. You specify the number of iterations for a specific loop, nest level, and you also kind of set what the number of instructions in that that loop body is. So you might do multiple instructions in one loop. So these instructions are used to, if you remember the code repeater that I showed at the front end of the pipeline, to program that code repeater with how many number of iterations the group of instructions need to run. And also, since we are using a scratchpad addresses, and if you remember the iterator table, if we deal with a nested loop and we need to operate on a multidimensional tensor, the iterators could be different for each dimension of the tensor. That's why we have the set index instructions for the loop, so that per each dimension of the tensor, or equivalent to a level of loopness, you define the iterators that need to be used for that specific level of loopness, so that at compute time, you'd use the correct indices to the iterator tables, get the correct offset and stride to get the address. All right. Another class of instructions that we have for the Tandem processor is kind of supporting mixed precision operations. What it means is that the data type that your systolic array supports can be different from the data type that your Tandem processor can support. Generally, for convolution, gem operations, you can kind of sustain lower bits. You can do 8-bit maybe gem operations. When it comes to these non-gem operations, you require higher data type. So the data types of Tandem processor and the gem unit could be different. So that's why we have this kind of data type cast instructions that you can cast different formats of data. For example, if it's the output of the Tandem processor, cast it to the correct format that the gem unit can use it for the next operation. Right now, the ISA right now supports fixed point data type cast operations, but can be extendable to support fixed point, to bring floating point, to floating point, or different formats. Now these are the synchronization instructions. So the way that the execution happens, as I said, it's a sequence of multiple layers. There could be a convolution followed by a set of non-gem operations. So you need to have instruction boundaries across these execution. And that's why we have the synchronization instructions that define the boundaries of instructions that need to be dispatched to the gem unit, that needs to be dispatched to the Tandem processor. And you use these instructions to inform the other unit that, okay, the execution is done, I'm done with this data, now you can use it for the next kind of cycle of operations. And since we are using the output buffer for the Tandem processor, we also introduced these instructions. You don't want to stall your gem unit since your Tandem processor is accessing the output buffer. So the Tandem processor might consume the data on the output buffer, but still do further computations. But you want to release the output buffer for the gem unit as soon as possible so that you can start doing the computations on the next time. So when the Tandem, in the sequence of instructions, it reaches to this instruction, it means that the Tandem processor has consumed all the data on the output buffer. Now it releases to the gem unit to completely take that output buffer for the next tile of operation. And finally, these are the instructions that we use for program the data access engine to get the data from off-chip memory and store the data from the on-chip memory to intermediate buffers to the DDR memory. And there are two classes of instructions here. We have some instructions to handle inter-tile walk, because again, you are bringing the data into tiles. So you want to make sure that you are walking over these tiles correctly, getting the next tile addresses correctly. So these are the instructions to program the data access engine for inter-tile. And these are the instructions. Now you know where the tile starts, but you need to walk over that tile. So these are the instructions to program how you walk over a tile of the data. So that's why we have inter-tile and intra-tile walk operations. So any questions on the kind of overall on the ISA? Yeah.
Are you able to change the primitives that you have? Like for example, say I have no need for a division. Can I, in the generator, is there a way for me to just remove the division? And
oh, you mean just remove the at the hardware generation? You just remove the
and have the compiler also, you know, be able to change the ISA so that it.
So the ISA is extendable. You can add more instructions to it. Removing instruction from ISA, I don't know what the point of that would be.
So for example, like a division's expensive, right? And I say my network, I have no divisions, I have no need for it. Is there a way for me to remove the division hardware and have the compiler also just work?
I think it could be, we can do it. I mean, right now we are not maybe doing
that's
this.
Actually a good
But
point.
that's a good point. It can be.
You can add like defines while configuring.
Yeah.
And then what, because you need to manually go to the RT and remove it right now. The way we have implemented floating versus fixed point is we have defines. You can choose between them. But what we can also do is at a final granularity, what are the operations? So that would actually save power by sense, I think.
That's actually a nice point, I think. That's something that we should add so that you can remove instructions that you don't need. Actually, it also opens up slot if you want to extend the ISA with newer instructions that you want. So that's a nice point, yes.
It's just also removing the whole functional unit.
Yeah. So that's what Rohan was talking about defines. So that you set defines in the RTL so that you just remove that complete block from the RTL as well.
So can you go back to that synchronization part?
Yeah.
So when you are ALU is working, right? Like basically my question is when does a Tandem processor start reading the output of your ALU? Like when it is still doing some part of the computation, does it start reading from the scratch pad? Like,
sorry, I didn't exactly get it.
So you have a Tandem processor that, if I understand it correctly, it just reads it from the output of the vectorized register file, right? And reads that and puts that in the scratch pad.
No, there is no register directly accesses the scratch pads itself. So, but two types of a scratch pad that it directly accesses. Either it's output buffer or it's intermediate buffer.
Okay.
Intermediate buffer is localized to the Tandem processor. So Tandem processor is the only processor that uses that.
Okay.
But the output buffer is shared between the systolic array and the Tandem processor. And that's why we have this instruction so that you can release the output buffer as soon as you are done with it, so that you can fetch the next and compute the next tile of operations on the systolic array as soon as you're done with the Tandem processor is done. Alright, so as I mentioned, the Tandem processor, these are like kind of the blocks inside of it that handles the execution control, orchestration, handling the synchronization. And now I think we mostly talk about these things. I'm just gonna run through those real fast. As I mentioned, we have this sequences of execution of the layers at the compile time. Compiler decides what's the best way to fuse layers together. For example, fuse a convolution, we can add an review to kind of leverage software pipelining. And there is this double buffering on the scratch pads. We do it at the tile level. And so the way that it actually works, as I mentioned, you have these layer fusions. Right now, I think the compiler, if I'm correct, compiler supports, basically the heuristic that the compiler uses, starting with a convolution and ending with a non-convolution or non-gem operations. But that's something that can be extendable in the compiler so that you can have more variations of supporting these sequences of instructions. And this is like the way that as the software pipelining works. You use unified tiling schemes across the outputs and inputs of these sequences of fused layers. And you have, let's say, 2 tiles of gem, 2 tiles of non-gem operation, and just skipping through this and see how it is. You load a tile of data. The systolic array starts computing that tile of data. While it's doing the compute, you start fetching the data, if you need, for the Tandem processor from the off-chip memory. Systolic array is done with it, stores it on the output buffer. Now Tandem processor has its data on the output buffer and also the data that it might require from the off-chip memory on the intermediate buffer. Starts doing the computation. Now the gem unit is, whenever it's done, the Tandem processor with the output buffer, now the gem unit is going to bring the next tile and starts doing the computation of the next tile. And how the software pipelining happens, Tandem processor is done with it, store data to it, now gets the next tile of the data, to the second tile, and so on and so forth. So that's how you can leverage, kind of maximize the utilization on both of the accelerators, both of the processors. And this is the complete kind of instructions. I mainly went through the instruction formats for the Tandem processor, but these are also the instructions that we use for the systolic array to, as I said, to kind of configure those address generators on the on-chip, and also the off-chip memory interfaces to get the data at the tile level. And I think we are just running out of time on this section. So we went through the architecture side of it, and after the break, I think we're going to talk about how we do verification, how we do kind of data type conversions and things like that, and also the compiler Chris is going to talk. And we're going to have, like as I said, this specifically the Tandem processor, we're going to have a full talk on it on the main conference. And there we also discuss about some of the results as well. I think we didn't get time to go over there, but on the main talk, we have those kind of comparison data points and also see the Tandem processor. All right. See you guys after the break.